Hello everyone, and thank you for joining us. My name is Przemysław. I'm a senior DevOps engineer at CodiLime.
And my name is Arkadiusz, and I'm DevOps engineer.
During today's presentation, we will answer the question how to optimize test infrastructure to reduce complexity and cost.
We are going to walk you through infrastructure testing challenges and, most importantly, real-world scenarios of how our team tackled those challenges.
We will cover the problems we faced, the goals we set, the architecture we built, and the impressive results we achieved. I want to ask you one question. How many hours has your team lost in the last month waiting for a test environment, and how many of your PRs have been stuck by non-predictable infrastructure?
Today, we wanted to talk about our journey to reclaim control over our testing environments. We went from fighting for physical resources to a world of orchestrated harmony. And we want to show you exactly how we did it. Before we will reveal our solution, Przemek, why don't you start by telling us what kind of surprises may await us?
Sure. So let's start with the current challenges in testing infrastructure. The first problem we face in infrastructure testing is that our test suites are different. First, each test suite has very different resource needs. For example, Suite A needs 32 CPUs and 64 gigabytes of memory, while Suite C needs up to 80 CPUs and 142 gigabytes. This makes it hard to pack workloads well and schedule them on shared infrastructure. Second, we have network overlap problems. In our case, tests are executed on network topologies, so even if the topology changes, the main network range stays the same. So when we try to run multiple test environments on the same host, they network conflict. And because of these two issues, resource fragmentation and network conflicts, we are limited to running only one test suite at a time on each host. Another challenge is that testing environments are not consistent. Let's start with what looks like a correct flow. A test runs in a clean environment, it finishes successfully, everything looks fine. But in reality, it still leaves artifacts behind, like processes, configuration, or data. Now let's run next test on the same host. This time it starts in contaminated environment, and because of that it may fail even if the test itself is correct. And it can leave even more artifacts on node. Of course, we do have cleanup scripts, but sometimes they are not fully reliable. They can fail or they don't remove everything. And this makes the environment unpredictable and debugging is quite difficult. Another issue is bottlenecks in network test environments. There are three main reasons for this. First, we don't have enough test environments. Our infrastructure cannot keep up with demand. Second, the number of tests is very high. We run more and more tests as our system grows, which adds pressure on the environment. And third, the tests take long time to finish. So environment stays busy for a long time and block other tests to be executed. As a result, we see a growing queue in our CI system, in this case Jenkins. The graph on the right shows how the build queue grows over time, sometimes reaching very high levels. This means developers have to wait longer for feedback, which slows down the whole development cycle. Arek, based on your experience, can you explain what challenges we really faced?
Sure. We are going to look at a real-life case study here. To answer your question, let's break down the specific challenges and the core problem we faced. So, here's our current setup. We have our CI/CD infrastructure with servers to handle all the regression testing. Right now, when we trigger a batch of tests, the pipeline picks up the first set and pushes it to the servers. They start running, everything looks fine, but here's the catch. We have a queue of tests waiting, and we would love to push them to the servers immediately. The problem? We simply can't. The test framework is built in a way that blocks two tests from running on a single machine at the same time. Even if we force it, they would just fail. The result? Our servers are underutilized, tests are waiting, resources are wasted. Now that we know what the problem is, Przemek, how do we fix this?
Yes, but before describing the solution, we should spend a while on our project goals. So, based on these challenges, our main goal is to improve efficiency. There are two ways to look at this. First, we want better efficiency using the same amount of bare metal resources. In other words, we want to get more from what we already have. And second, we want the same level of efficiency using fewer resources. This means using less hardware, but without reducing performance or testing capacity. Less machines also mean lower costs and real savings. Both approaches focus on better usage, not just adding more and more machines, but using them smarter. Our goal is to move to fully isolated environment for each test suite. Every test should run in consistent base environment. That means the same runtime, the same libraries, and the same configuration every time. Nothing changes between runs. We want full network and data isolation. Each test environment should be fully separate, with no conflicts or overlap when running at the same time. And finally, we would like to remove the need for cleanup after tests. Instead of using cleanup scripts, environment should be short-lived and removed after each run. With this approach, tests become predictable, consistent, and safe to run in parallel, which actually improve both efficiency and scalability. Another key goal is to improve orchestration and observability of test suites. First, we want smooth integration with our existing CI/CD pipeline. Test execution should be fully automated and naturally fit into our current workflows without requiring the developers to change their habits. We want detailed monitoring of both environment and resource usage. This includes CPU, memory, and overall system behavior during test runs. And we want to analyze how resources are used across test suites. We want to understand usage patterns and find ways to optimize. With better orchestration and observability, we can make better decisions and keep improving efficiency. Now that we have our goals, Arek will show how we designed our test environment.
Exactly. I will walk you through how we turn those goals into a working environment. And it will begin, just like every great story, with the plan and the architecture. First, let's ask ourselves the question: how can we solve all the problems and actually hit our goals? Or to put it in another way, how can we run multiple tests simultaneously on a single server? Kubernetes comes to the rescue. The servers will become part of the cluster as so-called nodes, and instead of running tests directly on the operating system, we will encapsulate them in isolated pods. Simple, but we know simple solutions are usually the best. So let's look at the architecture behind this. In our setup, Jenkins is our CI system. We connect it to the Kubernetes cluster, starting with the control plane. Then we have our nodes, the same servers I showed you earlier. These nodes is where Jenkins actually triggers the tests, but now inside the pods. Now, a quick deep dive into the pod structure. It's one of the key elements in our solution. Each pod is an independent unit consisting of two containers. That gives us full isolation from the host. The first container is the Jenkins agent, and it handles communication and monitoring. The second container runs the test framework, and it is done using our custom image that we built ourselves. With this architecture, we are ready to go to start running the first tests. However, to make it production ready, we've added Prometheus and Grafana for metrics and full observability, plus a dedicated database. That was the turning point. We deployed this to the first team, and that's where the real optimization began. But there's one significant step from the perspective of integrating this solution with other teams' test environments. And this is ability to run different types of tests. Specifically, we support two main scenarios. The first, and our default, is a fully encapsulated virtual topology. Everything lives inside the pod. The virtual machines, the switches, the interfaces, and the test framework itself. It's a complete, self-contained replica of a network environment. The second type also starts with a virtual setup, but with a twist. It allows us to bridge an external physical device into the topology. This becomes our device under test. This is where it gets powerful. We can spin up a clean environment to verify physical hardware while simultaneously running other virtual tests in separate pods and all on the same node. This leads to the obvious question: how many of these tests can we actually run at the same time? To talk about the results, I will handle it back to Przemek.
Okay, so here are the results from our proof of concept. We run tests on nodes with 64 vCPUs, where each test suite needs 20 vCPUs. First, let's look at concurrency on the left. With the legacy solution, we can run only one test per node at a time. With the new approach, we can run many more. For example, on single server, we go from one test to 3 tests running at the same time, and on 10 servers, we scale up to 30 concurrent tests. Now, each test takes about 1 hour to complete. Now, looking at the total execution time on the right, we see a clear improvement. On one server, running 10 tests takes about 10 hours with the old setup, but only 4 with the new approach. On 2 servers, total execution time is reduced by half. This shows that better isolation and better resource usage allows us to increase parallelism and reduce total test time. Now let's look at production results. We see a clear increase in the number of concurrent tests as we scale the infrastructure. With 8 servers, we can run more than 20 tests at the same time. As we add more servers, the system scales linearly. With 29 servers, we run over 80 test suites at the same time, compared to just 29 before. This shows how the solution is effective and scalable. We use resources more efficiently and increase overall throughput. In production, this means faster execution, shorter queues, and much better efficiency. However, as we scaled, we also discovered a new problem: big pod starvation.
Yes. Let's look at another real-world issue that we faced. It happened after running tens of thousands of tests on this infrastructure. Again, we are in CI/CD environment, but now everything is running inside Kubernetes pods. Because we have Kubernetes, we can finally get serious about orchestration. We introduced different pod sizes. Now we are making granular decisions about workloads based on their needs. So, pods get deployed, tests start running, everything looks great. But then CI/CD pushes a big test, a massive topology that needs a ton of resources. It might even need an entire node to itself. Time passes, some smaller tests finish, and some space opens up on the nodes. But here's the problem. As long as even one small test is still running on a node, that big pod is stuck, because it's just too big. It requires too much resources, and Kubernetes won't schedule that pod. It has to wait for the node to be completely empty. And it gets worse. If Kubernetes can't place that big pod immediately, and a new small test pops up, that small test will jump the line and take the free spot. In result, blocking the big pod again. In the worst case scenario, if there's a continuous stream of small tests, our big test might get neglected forever. It just sits there, starving for resources. So again, we need a plan. And since this solution was already live, running on a production, every minute counted. So we started by analyzing what was already out there. Off-the-shelf scheduling software proved insufficient. First, it doesn't account for the order in which tests appear, and second, it doesn't take into account the duration of the tests or the uptime of the nodes. So we took advantage of Kubernetes flexibility and we built our own solution. We use Scheduler Extender as a base. It's a powerful mechanism for customizing pod scheduling without modifying the core scheduler code. We introduced a mechanism to detect what we call big pods, and we also added functionality to reprioritize pods waiting in the queue. This allows us to instantly prioritize tests that address very critical bugs. The results? Precision scheduling. Then, the entire system is streamlined, ensuring that no tests, no matter its size, gets left behind. Like I said, we shifted from just running the tests to making truly granular workload decisions. And on that note, I will hand it over to Przemek again to dive deeper into the resources data.
Okay, so let's look at CPU usage and how we improved estimations. So at the beginning, we set CPU limit based on calculations from test suite topology file. For example, we estimated around 18 vCPUs for test suite 1, but when we checked real usage, it was much lower than calculated. In this case, tests use about 10 vCPUs. This shows that our original estimates were too high, which led to inefficient resource usage. And by using real metric instead of static assumption, we can fit more workloads on the same infrastructure. This means observability helps us size environment correctly and avoid wasting CPU. So what is the impact of this optimization? On the left chart, we see that we ran 6 test suites in parallel on one node. This shows how much we improved after optimizing CPU usage. On the right, we can see the comparison between calculated and reduced CPU values. For example, in test suite 1, we reduced from 19 to 10, and in test suite 3 from 34 to 20. This reduction also allows us to fit more workloads on the same node. As a result, the number of parallel runs increased, for example, from 3 to 6 on the same node. Overall, we are using resources much more efficiently while increasing concurrency at the same time. And actually, this is where we unlocked real capacity. But to make all of this work well, we rely on observability. We use Grafana and Prometheus as our main monitoring tools. We monitor several key areas. Node level resource usage. We track CPU usage, free cores, and pod count on each node, so we can see how efficiently we use our infrastructure. We monitor high priority workloads. We track how many high priority pods and nodes are active over time, so we can understand how critical workloads impact the cluster. And of course, we look at detailed resource usage for test environments. For each test suite, we measure CPU, memory, throttling, network usage, disk usage, and many more metrics. And this allows us to compare real usage with requested resources and optimize allocation. We also track overall test suite migration status to our solution. We monitor how many test suites are already migrated and how many are waiting to be moved. And finally, we monitor Jenkins activity. We track the build queue and the number of running jobs. This helps us identify bottlenecks, especially when jobs are waiting for available nodes. All of this data is combined into dashboards. This helps us quickly find inefficiencies, reduce waiting time, and improve resource usage. Okay, let's summarize what we achieved by deploying our solution, highlighting our key successes and learnings. We want to show you the real numbers. First, we increased the number of tests running at the same time on single server from 1 up to 6. And as a result, we reduce resource usage. The same number of tests now needs 64% less servers.
We have increased efficiency because the resources we saved allowed us to run a total of 279% more concurrent tests. And all of this takes place in environments that are clean, predictable, and consistent. In addition to the hard data, we would like to share other successes and other lessons learned from this project. First, seamless integration with existing CI/CD. Some users didn't even notice a difference in where their tests were running under the hood, other than the fact that the test became just stable.
Yeah, we achieved a significant cost reduction and better performance. At the same time, we created a clean and stable environment. Users wait less for test results and no longer deal with unexpected errors. Because of strong test results, more teams are adopting our solution. And so far, we have executed over 150,000 tests without any infrastructure-related errors.
Besides to these successes, the key learnings are an important part of the picture. First, we had to went through all suites to resolve dependencies and include them in our container-based image. Also, we gained a better understanding of the limitations of Kubernetes scheduler through our work on custom scheduling mechanism. And we fully understand how our test framework works. As we mentioned, our solution works seamlessly, not only in theory, but also in production environments. And not just for a single team. Przemek, tell us more about the next steps.
Sure. So, as a next step, we plan to move to a cluster-wide network topology. The idea is to run each VM inside its own pod, which gives better control and flexibility. We will also add network isolation at the namespace level. This allows different test suites to use the same IP ranges without conflict, while still being fully isolated. And with this approach, we can improve resource usage by spreading workloads across the whole cluster. But unfortunately, this also requires some changes in testing framework, especially how environments are defined and deployed. But overall, this approach helps us scale better and removes many of the limits we had before. Okay, that's all from our side for now. Thank you for joining us today. We are happy to answer any questions you may have.
Exactly.
Okay, we have the first question. How do you handle CPU context switching when running multiple test suites on a node? This is a very good question. I will answer this, okay?
Mm-hmm.
Okay, so context switching may really affect performance on nodes. And we use on our cluster CPU pinning to reduce CPU context switching. This is option that we enabled in kubelet. There is a static policy for CPUs. And for the pods, we set CPU request equals to CPU limit. This gives the pods the guaranteed QoS class. And because of that, each test suite gets dedicated full CPU cores instead of shared. And this keeps context switching low and minimize something that is called a noisy neighbor problem.
Okay, so I will take another one. Did you consider any other options for resolving the issue with unstable infrastructure? Just curious, what was the main reason for choosing the presented solution? So I think the main reason was that the test framework required really different libraries for running the tests, and the servers that we received were running also really different OS versions, from Ubuntu 16.04 to Ubuntu 22.04. So in order to unify everything across such a wide spectrum of different machines, it would be really hard. And with Kubernetes, we have just one base container image that we are using. So we ensure that no matter the host under the hood, the pod and container running inside the pod, they always stay the same. I think that's the main reason.
Okay, the next question is, how flexible is the solution? Did you run it across different projects or environments? Actually, we run this solution only for one client, for one project, which use the same testing framework. But in reality, it can be used in any project. In our case, it was framework that builds network topologies for testing, but it can be used in any other project.
Can you give a follow-up on another one? Because it's
Assuming I want to adopt your solution to my test framework, what pre-work is required to make it happen? First of all, we should adopt our solution to your project. So we have to understand how your test framework works, what is your requirement for running our solution in your project. So you can ask us by email. Please send us an email and we'll answer your question.
Another question, how does your custom scheduler extender decide where to place pods on nodes? And how does its mechanism for detecting large pods work? So it's a pretty complex thing that it's done in steps. First of all, big pods is for us a workload that it's waiting in a pending state for too long in a Kubernetes cluster. And that waiting time is always due to the resources, because smaller tests are easier to schedule. So we have a mechanism that detects such a pod. The threshold can be customized. Then we label such a pod with a high priority label, and that triggers the mechanism that starts looking for a perfect or a best node for that pod. The best node is the node that will be available in the shortest time. And then when we found such a node, we are using a combination of taints and tolerations, all from Kubernetes, to precisely tell the Kubernetes that we want to schedule that pod on this node. And because we are using taints, it effectively blocks other workloads to be scheduled on that node. And last step is the scheduler extender itself, which is filtering high priority pods, and that scheduler extender allows us to do that precise pod placement.
Okay, that was last question.
Again, thanks for joining us today.
Thank you very much.
And probably bye-bye.